In this video, I will show you a few applications of parametric equations. If you haven't yet seen the previous video, you should probably watch that first. This video will make a lot more sense if you do. You can either click the link that appears in the upper right hand corner or find the link in the description. Let's begin with some facts and formulas that I want you to memorize. For an object that launches at an angle theta with the horizontal at an initial velocity v0, where g is the acceleration due to gravity at sea level, t is time, and h0 is the initial height, the horizontal distance traveled during time t, x of t, is given by v0 times t times cosine theta. The vertical distance traveled by an object is given by this formula. The first term represents the vertical distance traveled by the object if there was no gravity. However, because there is gravity, we have to subtract the distance that the object would fall if it were simply dropped. If you want the vertical position of the object as opposed to the vertical distance traveled, you must add on the initial height h0. The vertical position formula includes this constant g, which is the acceleration due to gravity. G is 32.17405 feet per second squared, or 9.80665 meters per second squared. Problem 1. A rabbit jumps across the floor at an angle of 83 degrees with an initial speed of 2 meters per second. So for this problem, theta will equal 83 degrees, v0 is 2 meters per second, which means that we will use the value of g of 9.80665 meters per second squared to match the meters per second. Part A. Write a set of parametric equations for the motion of the rabbit. Well, these are the parametric equations right here. It's just going to be the horizontal position and the vertical position. So here we go. X of t is going to equal v0, might as well just go ahead and put 2, t cosine theta, cosine 83. And then the vertical position is y of t, which is going to equal 2t sine theta, subtracting the 1/2 gt squared, and again I'm using this g right here, and then plus the initial height. He's jumping across the floor, so the initial height is 0, which we don't need to show. Part B. Determine how long the rabbit was in the air. Determining how long the rabbit was in the air is the same thing as finding the time it takes for the rabbit to reach the ground. In other words, we need to find time t such that the vertical position is 0. Setting y of t equal to 0 gives us this. We can solve this equation by factoring out a common factor of t. Next, we can find the solutions by setting each of these factors equal to 0. Well, this first little factor simply gives us t equals 0, which reminds us that the little rabbit was on the ground right at the beginning at time t equals 0. That's not what we're looking for. We're looking for another time when the rabbit is on the ground, and we will get that by setting the other factor equal to 0. So now we have this. All we have to do is solve this little equation for t. Let's move this term to the other side of the equation by adding it to both sides. Next, I'm going to do two steps at once. I'm going to multiply both sides by 2. That'll get rid of this 1/2 on the right, and I will have 4 on the left. But then I will also divide both sides by g, so expect to see a g show up right here. So t is 4 sine 83 divided by g. Let's put this in the calculator. But first, let's store the acceleration due to gravity into the letter g on our calculator in case we need to use it again later in the problem. So it's 9.80665. And let's hit store, and of course we will put it in letter G. Next we type in 4 sine 83 over G. So that's 4 sine 83. Make sure you are in degree mode. And then divided by g. So that's 0.405 seconds if you round up. Part C. Determine how far the rabbit traveled in the air. This means we need to find the horizontal distance traveled by the rabbit during the 0.405 seconds that the rabbit was airborne. So we need to find x at 0.405. So all we have to do is substitute this in for t. So we are about to type this into the calculator. However, I don't want to lose any decimal places here with this 0.405, which is really a much longer decimal, of course. So let's store this into the letter t so we don't lose accuracy. If we immediately hit store and then alpha t, it puts all these lovely decimals into the t. So now we can type in 2t cosine 83. So 2 alpha t cosine 83. Kabam! 0.098, let's call it 0.099. So the rabbit hopped 0.099 meters. Part D. Determine when the rabbit reached its maximum height. Well, the path of the rabbit's hop is a parabola, and the maximum height will be at the vertex of that parabola. Here's a fact that you should have memorized from Algebra 2. Given a parabola in the form y equals at squared plus bt plus c, the vertex will always occur at t equals the opposite of b over 2a. This is the parabola that represents the vertical position of the rabbit. Be careful, it's sort of backwards compared to this model. So the value of a will be the coefficient of the t squared. In other words, this is a right here. A is negative 1/2 g. Let's turn this into a decimal real quick. So negative 1/2 times g. So it's about negative 4.903. Actually, let's store this into letter A on the calculator right now. So store alpha A. Okay, now we'll write it down. Meanwhile, the b value is the coefficient of the t. So here's t right here. The coefficient is going to include the 2 and the sine 83. So b will equal 2 sine 83. 2 sine 83. And let's immediately store this into letter B. The vertex and thus the maximum height will occur when t equals opposite of b over 2a. So back to the calculator, opposite of b over 2a. 0.202. So the maximum height will occur at t equals 0.202 seconds. Part E, determine the maximum height reached by the rabbit. Well, this will simply be the vertical position at 0.202 seconds. So we are substituting 0.202 in for t in the vertical position formula. However, let's store this value of t as a letter in the calculator right now so we don't lose these decimals. So if we hit store and then alpha t, we get to use all the decimals. So now we type 2t sine 83. So that's 2, then alpha t sine 83 and minus 1/2 gt squared. And we already have g typed in. So minus 1/2 g t squared. (0.201 if you round up. So the rabbit reaches a maximum height of 0.201 meters. Part F. Sketch the graph of the parametric equations. Be sure to label your axis. So far I have labeled the horizontal and vertical axis on my graph, choosing an appropriate scale. For example, we know that the maximum height reached by the rabbit was 0.201 meters. So I have chosen to put 0.2 right here near the top. Also, we know that the total distance jumped by the rabbit was 0.099 meters. That's almost 0.1. So that's why I'm putting 0.1 near the end of the horizontal. At t equals 0, the rabbit is here at the origin because so far it has moved neither horizontally nor vertically. At t equals 0.202 seconds, the rabbit reached its maximum height of 0.201 meters. However, we never found the horizontal position of this maximum height. So let's find that now. The horizontal position of the rabbit is given by 2t cosine 83. So to the calculator, and t is already typed in for us, so we can just do 2t cosine 83. Horizontal position is 0.049 meters. So here's that point on the graph. At t equals 0.202, the horizontal position is about 0.05. So it's really close to here. And that maximum height, of course, really close to 0.2. We found that the rabbit is back on the ground after 0.405 seconds, having jumped a horizontal distance of 0.099 meters. On the graph, that's going to be right about here. So that is the complete path of the rabbit. Problem 2. Hank hits a ball when it is 4 feet above the ground with an initial velocity of 120 feet per second. The ball leaves the bat at an angle of 30 degrees with the horizontal and heads towards a 30-foot fence 350 feet from home plate. From this setup, we know that h0 is 4 feet, v0 is 120 feet per second, and theta is 30 degrees. Also, because h0 and v0 both involve feet, we know to use the acceleration due to gravity that is given in feet per second squared. Part A. Does the ball clear the fence? Well, we know the fence is 30 feet high, so we're going to need to find the vertical position of the ball, y of t, and see if it is bigger than 30 feet. The fence is 350 feet from home plate, so we need to find the vertical position when the horizontal position is 350 feet. So basically we need to start by finding t. We need to find the value of t that makes the horizontal position 350 feet. Then we can plug that into the vertical position formula and find out if the vertical position at that t is more than 30 feet. We know that the horizontal position x of t is given by v0 times t times cosine theta. We want to set the horizontal position equal to 350 feet, so that gives us 120 times some t times the cosine of 30 degrees. And that must equal 350. We need to solve this for t, so let's divide both sides by 120 and cosine 30. So t is equal to this expression. Let's type this into the calculator. So that's 350 over 120 cosine 30. 3.368 if you round up. So the ball will reach the fence 350 feet away after 3.368 seconds have elapsed. Next, we need to find the vertical position y of t at this time. We know that the vertical position of the ball is given by this model. We just need to substitute in all of the initial conditions and t equals 3.368. So it looks like this. We just need to type this into the calculator. However, I don't want to type in 3.368. This is a rounded number, and I don't want to lose these decimals. So let's go back to the calculator and store this longer version into letter t. So if we just hit store right now and choose alpha t, now we are using all of those decimals whenever we use the letter t. I also would like to store this value of g into letter g on the calculator. So let's type in 32.17405 and hit store alpha g. So I'm going to type in this expression, but I will put in t instead of 3.368, and I will just use the g. So that's 120 t sine 30 minus 1/2 g t squared plus 4, which is 23.604. Y at 3.368 is 23.604 feet, so the ball will not clear the 30-foot fence. By the way, on the AP exam, once you have defined your variables, you are allowed to use those variables in your work. So instead of writing down this expression, I could have written this blue expression in its place. We have defined V0 and theta and G and H0. And by writing y at 3.368 at the top like this, I've also defined t. So instead of writing all of this, I could have written this, which just saves me a few characters by not writing 3.368 twice. And that would have been just as good. Then I can just go straight to the answer. Part A asked whether the ball cleared the fence. Part B says, if so, by how much does it clear the fence? And if not, could the ball be realistically caught? Well, we found that the ball did not clear the fence because when the ball reaches the fence, it's at a height of 23.604 feet, which does not clear a 30-foot fence. Can the ball be reasonably caught? No. 23.604 feet is too high for someone to catch. Again, the ball reaches the fence at a height of 23.604 feet, so the ball cannot realistically be caught.